Welcome to Daily Papers.
Today we're talking about robots, specifically how to teach a very smart, very general-purpose robot to be good at fiddly, precise little tasks.
Right. Imagine you have this incredible robot that can understand commands like clean the kitchen. It can find the sponge, it can turn on the tap, but when it tries to put the plug in the drain, it just keeps fumbling. It gets it almost there, but can't quite nail that final, precise movement.
It's the last millimeter problem, and it's a huge challenge in robotics. Today's paper, RL Token, Bootstrapping Online RL with Vision Language Action Models, offers a really clever solution to this exact problem.
Okay, so let's break down that title. First up, Vision Language Action Models, or VLAs. What are they?
Think of them as the big, multi-talented brains for modern robots. They're a bit like the AI models behind chatbots, but instead of just processing text, they process vision, what the robot sees through its cameras, and language, the commands we give it, to decide on an action.
So you can tell it, hey robot, please fasten that zip tie. And by looking at the zip tie and understanding your words, it knows what to do.
Exactly. These VLAs are trained on enormous amounts of data. Videos of humans doing things, robot demonstrations, text from the internet. They come out of the box with a huge amount of general knowledge about the world. They're a jack of all trades.
But, as the saying goes, they can be a master of none. They're good at the big picture, but when it comes to the incredible precision needed to, say, thread a zip tie through a tiny slot, they often struggle.
And that brings us to the next part of the title, RL, which stands for reinforcement learning. This is one of the main ways we can help a model get better at a specific task.
Reinforcement learning is basically learning through trial and error. The robot tries to do the task, and when it gets it right, it gets a reward, like a point in a video game. When it fails, it gets nothing. Over many attempts, it learns the sequence of actions that leads to the reward.
The problem is, if you try to teach one of these giant VLA models using this method, it would take forever. The model is so huge and complex, it would need millions of attempts to learn. For a real-world robot, that's just not practical. Imagine the wear and tear on a robot arm that fails to insert a screw a million times. It's not sample efficient. It needs too many samples or examples to learn.
So, on the one hand, you have these big, knowledgeable VLA models that are a bit clumsy. On the other, you have this powerful learning method, RL, that's too slow and inefficient to train them directly. How do the researchers bridge this gap?
This is where their key idea, the RL token, comes in. Instead of trying to retrain the entire giant VLA model, they took a division of labor approach. They decide to freeze the big VLA model. It acts as a senior consultant. It has all the experience and provides a good, general plan for how to do the task.
So the VLA looks at the situation and says, okay, to fasten that zip tie, you should probably move your left hand here and your right hand here. But that advice might be a little bit off.
Precisely. Now we need a specialist, a junior employee, if you will, to take that advice and perfect it. But for that junior employee to work fast, they can't read the senior consultant's entire life story. They need a quick, condensed briefing. That briefing is the RL token.
So the researchers train a small, separate component to look at all the complex internal data of the big VLA and compress it into a single, compact piece of information, the RL token.
Yes, the RL token is a summary of everything the VLA knows and sees about the current situation, all packaged up efficiently. Then a second, small, lightweight model gets to work. This is the part that actually does the reinforcement learning.
So this little model takes the VLA's general suggestion for what to do, along with that compact RL token, and then it's the one that does the trial and error practice. Because it's so small, it can learn really, really fast.
That's the recipe. The big VLA provides the general knowledge and a solid first guess. The small, lightweight learner uses that guidance to rapidly figure out the final, precise movements needed to succeed. It's not learning from scratch, it's just refining an already good plan.
So does it actually work in the real world?
It works incredibly well. The researchers tested it on 4 really tricky tasks for a robot: installing a screw with a screwdriver, fastening a zip tie, plugging in an Ethernet cable, and inserting a power charger.
All things that require sub-millimeter precision.
And the results were fantastic. Their method, which they call RLT, improved the speed on the hardest part of the tasks by up to 3 times.
For the screw insertion task, which the base VLA was really bad at, the success rate jumped from just 20% to 65% after only a few hours of practice. That's a massive improvement from a bit of focused practice.
But here's the coolest part. The robot actually started discovering strategies that were better than the ones that it was shown by human demonstrators.
What do you mean?
Well, for the Ethernet plug task, the original VLA would often sort of poke at the port, back up, readjust, and try again. It was hesitant. After training with RLT, the robot learned to approach the port and, if it met resistance, to apply a little pressure and give it a slight wiggle.
Like we all do when a plug won't go in.
Exactly. It's a fluid, confident motion that exploits the physical compliance of the objects. This strategy emerged purely from reinforcement learning and allowed the robot to complete the task even faster than the human experts who provided the initial demonstrations.
That is amazing. So the robot isn't just getting better at copying humans, it's discovering more effective robot-native ways of doing things.
That's the takeaway. This RLT method provides a practical and efficient way to make generalist robots truly useful for delicate, real-world work. It elegantly combines the vast knowledge of a huge pre-trained model with the fast, focused learning of a small, agile one. It's a huge step towards robots that don't just get stuck on the last millimeter.